Hey guys, what's going on? So today we're going to do an integral question. They want us to use Fundamental Theorem of Calculus to find the derivative of the following function. So I spiced it up a little bit. I made it a little bit harder than it needed to be, or than it was, because it doesn't make any difference. I just want to show you that you can handle a lot more than you think you can. So if we're taking, okay, let's just look at this for a second. So this is the integral. So they want to know the area under this function from some kind of arbitrary spot, 1 minus 6x, to another arbitrary spot, x squared. Okay, well, that might be kind of confusing to do, because that means we'd have to find, either use some Riemann sums to find this thing, or use Fundamental Theorem of Calculus, which is going to be a lot better, and then we got to take the derivative of that. So, okay, let's try and piece this together. So I've rewritten the function here. Okay, now, the Fundamental Theorem of Calculus tells us that we can compute this integral, this whole thing, as long as we know an antiderivative for this thing here. So I just use it's going to be a function, right? The antiderivative is going to be a function. So I just use the letter A to denote the antiderivative. Whatever it is, I have no idea what it is, but let's say whatever it is, it's A. So Fundamental Theorem of Calculus says that we have to evaluate it at x squared, which is the top last bound on our interval, our x interval, and minus their antiderivative evaluated at 1 minus 6x. Okay, that's really... it doesn't tell us much, because we'd have to know that antiderivative to know this. But luckily, we don't want to know the integral here. We want to know the derivative of that. The derivative of all this stuff. Well, the derivative of this, that x is not supposed to be in the exponent, is equal to d by dx of g of x. That's what the derivative is, where we're taking the derivative with respect to x in this case. G of x is just this long stuff that we got from up here. Okay. So that means if we're taking the derivative with respect to x of big G of x, that means we're taking the derivative with respect to x of all of this stuff here. Okay? Now, derivatives, like integrals, split over differences, sums and differences. So this is just equal to the derivative of the first guy minus the derivative of the second guy here. All right, this is where things get kind of interesting. Just a note, by the way, if one of these were a constant, if this thing here was a constant, like x squared was like a 4 or a 0, then the derivative of this would be 0, because an antiderivative evaluated at a constant is just going to give you a constant, no matter what your antiderivative is, no matter what your constant is. Okay, as long as we're working in one variable. And so a derivative of that is going to be 0. So that would be 0 in every case. That's an actual number. So I made this one a little bit harder with an actual value here. So if we take the derivative of a function, we have to use the chain rule, right? That's like taking the derivative of sine of x squared. That's a function sine of a function x squared. If we take the derivative of that, we have to do cosine of x squared, but then we have to multiply it by the derivative of the inside stuff. Our antiderivative is a function. Like I said before, I don't know what it is, but it's a function. And we're inputting a function into it. So if we have to take the derivative of this whole stuff, we're going to get the derivative of the antiderivative evaluated at x squared times the derivative of x squared. Okay? And then same thing over here. So we get the derivative of the antiderivative evaluated at 1 minus 6x times the derivative of 1 minus 6x, which is just negative 6. Okay, now, derivatives and antiderivatives work very nicely together. If you have an antiderivative and you take a derivative of it, you get back what you started with. They undo each other. Okay? So, here we started with the antiderivative, and then we're taking the derivative. We're just going to get back what we started with. Well, this was what we started with. We started with u cubed over 1 plus x plus u squared. So if we take an antiderivative of that, and then we take the derivative of our antiderivative, we're going to get this back, okay? Except it's evaluated at x squared, not u. It's evaluated at x squared. So notice how this thing here looks exactly like this stuff up here, because all we did, again, was take an antiderivative of this and then take a derivative of that. And then we get that, except for the fact that the 2x is there. Okay? Minus, and then the same thing goes here. It's the same thing here, except it's evaluated at 1 minus 6x. So that's why there's 1 minus 6x's in there, and then the negative 6 because of the chain rule. And that's all there is to it. Except for I didn't make the colors go. Jeez, you guys must have been so angry. So yeah, that's a basic, well, not so basic. That's kind of more the harder integrations using the Fundamental Theorem of Calculus, because it's got that chain rule in there. But just know that whenever you're given a question like this, that's got you're taking the derivative of an integral, you're probably going to be using the fundamental theorem of calculus. And for any test or exams, assume that you're going to get a question like this with where the bounds are weird things. And you might even get like a sine x here or something like that. It would work exactly the same way. So use this one as a guide for how to do those problems. Anyway, hope that helps. Shoot me an email or whatever if you want to set up sessions. Facebook me any questions on the learning group that I have. That's all free. Yeah, hopefully this helps, and we'll catch you on the next video. Pieces.